So if you guys remember, we talked just last time about what? We talked about what?
Memory.
Registers.
People.
And then, we build what? Memory. And, to be very precise, what we built last time, it's something can act like
Data bus.
RAM. So what is RAM?
Random access memory.
Exactly.
Yes, sir.
Random access memory. So is this actually make sense to you guys?
So people.
Yes.
So people's random access memory or SIPO.
I mean, it is just a random access memory. But in general, what we use registers, and the configuration was people, and we had decoder, and we have multiplexer, right? That's basically the ingredients, right? So normally, this is actually used for building something in the computer architecture. When you will go to ECE2300, you're gonna be taking something that's called register file, or they call it GPR, which is a general purpose register. General purpose register. We can look more into processors, but once we finish, the rest of the content. Okay. Anyway, now, if you noticed, if you would like to think about what type of operation that computer has. So the operation we learned, there is addition, there is subtraction, there is multiplication, and there is division. Right? Those are the most important arithmetic operation. But we agreed that everything at the end of the day in the computer is what? Adding. You guys agree?
Yes.
Yes. Yeah. Choose complements.
Yes. So C equal A plus B. C is A subtracted from B, which is basically A plus B complemented plus 1. End of the day, turn it to be adding. Right? Now we're gonna have another aspect. It's called logical operation. Because normally the central processing unit, the CPU we have, it has something that's called ALU. Have you heard about this term before? ALU.
The arithmetic logic unit?
Yes, it's arithmetic and logic unit. This is the computational brain in the computer. ALU, arithmetic and logic unit. So we already covered the arithmetic. We need to cover the logical part. What type of logical that we actually need to do the logic sense? Like, comparing. And we build the comparator, right? Extending values. And we discussed this before, right? If you are unsigned, we extend this, say that I have a value is 16-bit, right? And I would like to represent it in 32-bit, and it's unsigned. What I'm gonna do? I'm gonna bring this 16-bit and followed by padding of zeros here of 16, then that will be 32. You remember that? We discussed this in chapter 1, right? Then there is actually signed data, which is mean that if I have 16, the last bit will be representing whether they're gonna be positive or negative. Then if I would like to extend it, it will be what? You bring the 16s, and then you bring the other 16s, and this will be filled with what? With the replica of the most significant bit here to reserve the sign. So we need like a unit to do this. This unit will do something that's called concatenation. You're gonna see this in Verilog, VHDL, and all this, how those description languages. Now we need to look into the logical other logical. What other logical we have? We have something is called shifting. And this shifting is happening in two parts, logical and arithmetically. And we have another aspect, it's called rotation. So I'm rotating right or rotating what? Left. And of course, rotation is from the same family of the logic. So if anybody asks you what type of logical operation you have, it's gonna be shifting, rotating, logically, or arithmetically shifting. Let's see what is this. Let's at least understand the concept, and then we can start building it. Okay. So imagine that I would like to go into the logical thing first. Right? So shift, it can be shift logically right, or shift logically what? Left. What does it mean? Imagine the following. We already understood there is something called register. Do you guys agree? So now imagine that I have a 4-bit register. So 1, 2, 3, B0, B1, B2, B3. What are those? Are the cells inside the register. And we agreed from the last lecture that, what is the definition of the register? Is a bunch of flip-flops are sharing the same what? Clock. And if you remember in one of the slides, I just made it like that. So that means all of them have the same clock. Do you guys remember that?
Yep.
Okay. So now if I would like to logically right shift. So that means I'm shifting towards the right. So rules in the shifting, right? We push towards the right direction using 0 or 1, and normally 0 is a common candidate. What does it mean? It means the following. It means that I push toward the right using what? Zeros. So what does it mean I push toward the right, using zeros? Let's see. So now I'm gonna take this example as it is, and I put it here in front of me, right? 1, 2, 3, B0, B1, B2, B3. So I'm shifting towards what? The right. That means towards this arrow, right? Everybody agree? So I'm pushing with 0. Here is the 0 in my hand. Now I'm actually feeding the register with 0 and replacing location. So what does it mean? It means that if I shift logically right 1, that means I shifted 1 time. So end of the day, that will be what? 1, 2, 3. So gonna be here 0. B3 will be here, and then B2 will be here. B1 will be here, and B0 will be what? Spelled out. Spelled, there is no D. So that means I kicked it out. So I'm not reserving the bit. I'm not what? Reserving it. That means I lost it. So is it clear so far what I'm doing?
So where did the B0 go? It just went out somewhere, so we can't retrieve it anymore?
That 0 is coming from outside. Now we are talking about the logic. After that, we're gonna talk about how it's gonna be implemented. You understand what I'm saying?
Okay.
So now so how many times this thing it can be shifted? As much as I want, but literally I can shift up to 4 because I can shift up to the maximum size of the register, right? So that means if I shift right 2, that means 1 more time shifting this. So I will take this into my consideration like that. 1, 2, 3, right? I have the 0 in my hand. That will be placed here, and that 0 will be here. That will be B3, and then gonna be B2, and then this guy will be what? Spilled out. Then I have here shift right 3, which is basically 1, 2, 3, And then, I have the 0 here in my hand, so I put it there, and then that 0 will be here, that 0 will be here, that B3 will be here, and that B2 will be spelled out. Then, if I go also one more time, shift here logically, and here is 0, then, I will do the same, and it's gonna be 1, 2, 3, 0, and then that's 0, and that's 0, and that's 0, and that would be out. So end of the day, I cleared up the register after 4 times of what processing. Of course, if I start looking into this circuit, I need to learn the lessons out of it, right? I need to see what exactly I'm benefiting out of that, right? How I'm gonna do this, I need to alter that B0 and B1 and B2 and B3 with values. So I can see what is this will happen, right? And on top of that, if you noticed, the way I'm keep pushing, it looked to me like serial. Do you guys agree?
Yeah, so it looks like serial
It
in,
can be
serial out.
CISO or CISO.
Okay.
So, best traditional way of shifting is to use CISO or CPO, right? CISO or CPO what? Register configuration, right? Because, you keep pushing like this with 0. And then, if you want, you can read what parallel, or you can just read serial out. And we learned last time, what is the pros and cons, how many cycles and all these things, right? So far, so good. But there is something else also we are learning, which is mathematically. Which is what? Mathematically. What is this mathematically? Let's learn together. So, if I filled my register with a value, and this value is going to be 1, 1, 1 like this. It's going to be 1, 1, 0, 0. So what is written in front of us in this register? Somebody can tell me. 12. C, right? So in hexa, this is C, which is 12 in decimal, right? Everybody agree with me? So if I push shift logically right 1 now, what will happen? Shift logically right 1. So basically I'm gonna have what? 0 coming out, that 1 will be here, that 1 will be here, and the 0 here. So the value in front of me is what?
6.
So what does it mean? Shifting right is dividing by 2 without rounding. That's right. So note, shifting logically towards the right direction means what? Dividing the value in the register without rounding. Somebody will tell me, what do you mean by without rounding? I will tell you. Imagine that, imagine that, I have here written 1, 2, 3 like this, right? 0, 0, 1, 1. So here's 3, right? So if I push it shift right and logically right 1, end of the day, that will tend to be what? 1. But Dr. Ali said that it's going to be divided by 2. Yes, because 3 divided by 2 is 1.5. I haven't what? Look into that fraction, and I just took what? 1. In the case here, it was 12 divided by 2. It's even. So end of the day came what? So is it clear to everybody what's actually the benefit of using shifting towards the right?
Yes.
What type of application people use for the shifting right? My PhD, it was in security, not in cybersecurity. I mean, all of this is, whatever, it's buzzwords. But, the most important is the mathematics of the security, which is called cryptography. So my PhD was in cryptography. So anyway, the cryptography is basically the mathematic algorithm used for encrypting data. And there is something in encryptions using the shifting and rotation for increasing the security margin. So one of the possible application will benefit from the shifting is what? Crypto. The second.
Could you say that one more time?
Huh?
Could you say that one more time?
So, crypto, it has a bunch of encryption schemes, right? Crypto is the mess of the security. So, crypto, you are talking about public key algorithm, you are talking about symmetric key algorithm, you are talking about digital signature, you are talking about security protocols, you are talking about post-quantum security, you are talking about quantum crypto, all of those guys from the same family, which is crypto. All of this crypto, some of the tricks we are using in the crypto is actually shifting or shuffling and rotating. The reason for that is actually to increase the security margin of the function, so it will be very hard to be broken. So shifting and rotation, some of the operators we are using in a computer, so it will increase the security margin of the primitive. Okay, so that primitive, actually we call it S box, substitute box, which is very famous, and something is called AES, Advanced Encryption Standard. I'm gonna start teaching a new course I developed in the coming spring for crypto and chip. They're gonna be 4,011. Okay, sounds good. Anyway, what other application? Imagine what other application we are using for shifting. Multiplication. Can you imagine?
Yeah, you shift it left.
Multiplication. There is very famous methodology used in multiplication. It's called add shift method. It's called what? Add shift what method? Oh, let's see, my screen went black out. 1 second. Yeah, we're back. Anyway, so add shift method, imagine the following. You are trying to multiply 13 times 14, right? So what is 13 in math, in binary? 1 0, oh sorry, 1 0 1 1. What is 14 in the thing? 14 should be
1 1 1 0.
0 1 1 1, right? So when you multiply this together, how are we gonna do it? Somebody can tell me. Basically, what you are doing, you say 0 times 1, 0 times 0, right? 0 times 1, 0 times 1, right? Then you will shift. Did you see that? You will shift. So you move here, right? And then that 1 will be here to gonna be 1 0 1 1. Then that 1 will be here. So gonna be here what? 1 0 1 1. Then that 1 is gonna go there. It's gonna be what? It's gonna be here 1 0 1 1. And then you will start doing what? Adding. Add shift method, right? So end of the day, there is some places here in this multiplication I don't need it, because I know 0 times the value would be what? 0. So that's why they invented something is called add shift method. They invented something is called add shift method, which is basically using what? Addition belong with what? Followed by what? Shifting. So adding, shifting, adding, shifting. That makes sense? Do you guys like me to do an example for it?
Yes.
Just give me 1 second. I have to find you an accurate example I have in one of my documents, so you guys will fully understand what I'm saying. Excuse me. It should be in 7.
Professor, can you explain your shifts and how you did those shifts? I'm confused.
No, don't worry, I will confuse you. So, do you remember when you said, 13 times 14, what are you doing? Can you tell me?
You're multiplying.
So you say 3 times 4, right?
You
And
multiply the ones, and you multiply the tens.
Exactly. So then, you're going to go this 1, then you're going to go to be here like 3, and you're going to be here 1, and then you start adding. Do you agree? Hello? Can you hear me?
Sorry, my brain can't process. Wait, what?
What I'm saying that, look what I did, right? If
Yes.
this is the decimal multiplication, right? How you multiply it.
Yes.
So, and at the end of the day, what you're doing here, you shifted, right?
Yeah.
Second, because, the weight is different, right? This is, the first digit, this is the second digit. So everybody, every digit, it has its own position, right? Then you start adding, accumulating. Anyway, I will show you the add shift. So in the add shift, what you are doing, you can do the following. Okay, I'm gonna do this example of the 13 and 14. So imagine that 11 times 13, 11 times 13, right? So I'm gonna put 11 in M and I put 13 in Q. Okay, then my output, it should be what? It should be written in the register M and Q together. You know what? Let's call it AQ. I'm sorry, AQ. So AQ. Why? If you guys remember, I think the first midterm, right? I told you multiply, build a multiplier, and that multiplier will be 2-bit, right? And then, if you guys remember, when you start making the output, it was like a 4-bit, while each of them is 2-bit. And I told you the explanation after that. Basically, when you do multiplication, you check number of bits in each of the operands and the operators, I'm sorry, and then you will add them together. That will be the output. Do you remember that? Hello? Do you guys remember that? Again, imagine A is 4-bit. Imagine B is a 5-bit, right? I'm looking for C, which is coming out of this multiplication. My question, C will be represented in how many bits?
10-bit.
Huh?
Yeah, 10-bit.
Why 10?
Can you go to 9-bit?
5 plus 4 is gonna be 9-bit.
Is there such thing as a 9-bit? Oh, I guess there is a 9-bit. Okay.
That's fine. So anyway, I need to show you the add shift stuff. So in add shift, end of the day, you already have here like a register thing. So you have here C, and then you already have A, and you already have Q, right? I know A and I know Q, right? So this M, I'm sorry. This M and this A and Q. So what is this? And here's M. So it's basically, we are shifting and we are testing the bit we are spelling out. And I will show you in the normal traditional way, what does it mean? So, now, if I would like to process add shift method in a computer, just learn this, okay? Add shift method in a computer. Why we have add shift method? Add shift method is actually neglecting the value will be times 0. So for instance, in the example we have here, what the heck? What happened with my ear? 1 second. My screen went off. One second. What? You guys cannot see even my screen. Can you guys hear me? Hello?
Yeah.
Yeah, now it's working. What the heck? It's a glitch. Anyway, so add shift method, the trick is basically to do what? Anything multiply 0, I don't need it. It's like a redundance, right? Because, at the end of the day, when I will start adding, I will add 0. So, why I add something to 0, It's just like burning my battery, right? So basically what I'm doing here, you have to have a couple of things, right? I'm multiplying M times Q, and the output will be written in A and Q. Okay, so what is M? M here is 11, right? What is 11 in a value? Is 1101. Do you guys agree? What is Q is 13. 13 is what? 1011, right? Normally, I put in A as a register. Now it's register. It's gonna be same values. So the values is gonna be initialized as 0. So 1, 2, 3, 4. I'm gonna do shifting because it's called add shift. So initially I start shifting with what? With 0. Sounds good? Then I have here comments. What is this comments? In the comments, when I start looking into that bit, the bit I'm spelling out, right? If I find this bit equal 1, I shift and add. If I find it 0, I will just shift because I don't need to add. What does it mean? You can start looking to my example here, right? What I did here, I applied 0, and then I start accumulating this together. Then I move one more here. Then I start accumulating whatever written here with here. Then I move one more here, and so on and so on. So I checked here and I found 0. So in that case, I just need to do what? Shift, because I don't care that much about this line anymore. This is basically the process. Let's do it together. So anyway, now what I have, I found this is equal 1. So equal 1, that means I do what? I accumulate. I accumulate in A. So basically, I would say A is equal A plus M. Okay, so what does it mean? Excuse me. It means that, A plus M, so 0 plus 1, 1, 0, 1 is what? 1, 1, 0, 1. Do you guys agree? And the value here will be still the same. And then, I have here 0 as I want. Then I do what? I shift. I shift towards the right. So let's shift toward the right. So that 0 will be here. That 1 will be here. That 0 will be here. This 1 will be here. This 1 will be here. That 1 will be here. This 1 will be here. That 0 will be here. That 1 will be what? Spelled out. No more exist. So I shifted. Now I start looking into the bit exist in the queue. I found it 0. I found it what? Huh? I found it 0. 0, that means I'm not adding. Why I would like to add something would be multiplied to 0. So I just apply shifting. So in that case, I will start shifting. Shift one more time. I have here 0. So I will shift with 0. That 0 will be here. That 1 will be here. That 0 will be here. This 1 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 will be there. 0 will be out. So I shifted. Now I found here what? Huh? Hello?
1. So
1.
yeah.
What does it mean? I'm gonna do what? Accumulate A with M, and I put it in A, and then I shift, right? So now I will do what? It's gonna be A equal A plus M. So A is what? Is 2 plus what? This value. What this value will bring me at the end of the day? Somebody can tell me what the value will be written there. It's gonna be 1, 0, 1, 1. Right? It's added 0 plus 1, 1. 1 plus 1, 0. And then the 1 will be the carry. It will be added to the 0, gonna be 1. So far, so good, guys. And that value will go down here. 1, 2, 3, 4. Now I need to shift. So I have to shift. Let's shift it together. Shift it together. Gonna be what? 0 here, 1 here, 1 here, 0. And that one will be here, 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 and that one will go out. See a queue shifting. Now we're gonna do this process one more time. That one is exist, right? So what does it mean to me? Then I'm gonna add and shift, right? So A equal A plus M. So I have this is 6. 6 plus what? Huh? 6 plus 11. 6 plus 11, what is the value will be? Somebody can tell me. 6 plus 11, what will be? So I have here 1, 1, 0, 1, 0, 1, 1, 0. Add it together. 1 plus 0, 1. 1 plus 1, 0, and I have 1. That one will go here. 1 plus 1 is gonna be what? Z1 I have 1, that one will plus gonna be Z1 I have 1.
Sorry, are we still doing 13 times 14, or is this a different number?
Oh, sorry. I make it 11 times 6.
Oh, okay. So M is the 11 there. Okay.
Yeah.
Sorry.
So anyway, so now you know after I added A with M here, right? What the value came out? 5-bit, right? Where I'm gonna add them, it's gonna be here to be 1, 1, 2, 3, and then the carry is gonna be 1 because it's a 5-bit, right? Then I will leave those go down as it is 1, 2, 3, 4. Now it's a turn to do what? Shifting. Somebody will ask me how many times I'm gonna do this. 4 times. You know why 4 times? Because the size of this M is what? 4-bit. So in general, I'm gonna look also here, and I found it also 1. So then you know, no, I haven't shift, so I have to shift. Sorry. So shifting is still gonna be 1. So gonna be here, you shift here. This time, you know, that 1 is exist here. So I have to shift with 1. So then it's gonna be 1, and then gonna be here 0. Here we're gonna be 0. Here we're gonna be 0. Here we're gonna be 1, 1, 1, 1. And I have here 1. So then I will do the process twice again, which is basically A equal A plus M. And then I will do CAQ. End of the day, it's gonna be 1, 2, 3, 4, and then 1, 2, 3, 1, and then you know, this is the value I have, and then you know I have 0. So end of the day, you know, you don't need this step actually because I had already 4. Look, 1, 2, 3, 4. Yeah, it's 4. So anyway, if you start looking to this value 1, 1, 1, 1, 1, 2, 3, 1. If you calculated what the value will be as a decimal. So gonna be 2 power 0, 2 power 1, 2 power 2, 2 power 3, 2 power 4, 2 power 5, 2 power 6, 2 power 7. So end of the day, this is actually 143, which is basically, if you multiply 11 times 13, it's gonna be 143. So what I want to show you, this is basically one of the advantage of what shifting towards right, which is applied in the add and shift method for multiplication. Any questions so far?
Yeah, I think you lost me when you're shifting the second time.
Okay, let's do it again. There is no problem. Where did I lose you?
After you shifted, like after you,
Here?
I understand. Yeah, it's after that one.
Yeah,
because I see that you put the 0 in.
Yeah, I looked here 0, right? I found this 0 there.
Yeah.
If I find 0, that means the next time I will do what? Just shifting. And that was the next time.
So if the output is 0, then you do a shift.
It's not the output. You mean the significant bit in Q.
Okay. So it's not the spill out.
Not the spilled out.
Okay.
The existing.
Why are you plugging in ones? Does it change ever, or is it always ones?
No, look, it changed. Look, it keeps changing because you keep pushing, right? In our case, because you know came 1, 1, 1, 1. So every time I will shift, I will get 1 in this significant until I clear it up, right?
No, I mean like so you have when you're shifting it, right? You're adding a 1 at the very front, or at the, at the very in the very front. Does that ever change?
I didn't add 1. Where I add 1?
Well, you shifted 1, like so.
Oh, you mean here?
No. So at the very top, right?
Okay.
If you look at the very top where the first box is, where you boxed it, right? No. I mean the box that you made, the bottom box.
Oh, this one.
Yes, yes. So when you shifted it, right, you have 1, 1, 1, 0, and you shift it. So now you have another 1 at the very end, though. Now.
Yes. Then I look at that 1, and then I decide what I'm gonna do.
So. But it's always 1, right? Does it ever change to a 0?
It changes, of course. This situation. Let me do another example. Let's have another number. Okay.
Okay.
The other number can be let me think.
Let's just do like something simple, like 6 times
1, 2,
8.
3, 0, 7 time 2. Right? So I know that 2 is gonna be 0, 1, 0, 0. Do you agree?
Yes.
Yep. Sounds
Okay,
good.
let's do this. So gonna be here what? It's gonna be here Q, A, C, and M, right?
Yes. What's A? I didn't understand what A was.
It's accumulative. Do you remember when I told you that when I have two operands, right? It's two registers. One is basically 4 bits and one is 5 bits. What the output will be?
9-bit.
It will be the addition of 2, right? That's basically what I do. You know, those together are the registers. When they will concatenate at the output, it will be the output. That's called A. I just make it called A. You can call it whatever you want.
Okay.
So basically the pile, the new pile, right?
So is 7 and 2 M and Q?
Yeah. So, you know, 7 is going to be here. 1, 1, 1, 0.
Okay.
A initially started 0, right? C initially started 0. M is basically 0, 1, 0, 0. Do you agree? This is what we did last time, right? Hello?
Yep. Yep. So we're
Now,
gonna add
we're going to start, look. First time, I found this equal what?
1.
So what I'm going to do?
You're gonna
It's
add
going to be A equal A
A
plus
plus
M.
M.
So I'm going to take this as it is. It's going to be 1, 1, 1, 0. And that will be added to this. It's going to be 0, 1, 0, 0, and then 0. And then, you know, and that's it. But, you know, normally when I found one, it should be second step to also shift.
Yeah.
So now I'm shifting. So it's going to be CAQ. What does in CAQ? That means I keep pushing from C towards Q. That means shift right. So I shift right like this, right?
Okay.
That means, you know, that's 0. You know, I have zeros a lot in my hand, right? So 0 here. So that 0 will go here. This 0 will go here. This 0 will go here. This 1 will go here. That 0 will go here. This 0 will be here. That 1 will go here. This 1 will go here. And don't worry about that 1 went out.
Oh, I get it.
By that one, I don't want to see you, right?
Okay. Okay.
That's why it's called spelled out, right? Anyway, so yes.
Why are we always pushing a 0?
What? That's called logical shift. So that's why I push with 0. Do you remember in my definition?
Oh, okay.
Yeah.
No, I said somewhere. You guys, here, we push toward the right direction using 0 or 1, and normally 0 is the common candidate.
And we still push this one 4 times, right? Because there's 4.
Yeah, we gotta do this,
Okay.
you know, till the end. Don't worry. Anyway, so you know, we finished the first step. Are we done? Nope. So we have to do the second step, right? Second step. I found this equal what?
1.
1, so you
That
carry
means
it
what
down.
I gotta do?
A plus
Same
B.
thing, right? So
Yep.
it's gonna be A equal A plus M. So A plus M. In that case, A is it changed, right?
2.
So gonna be 1 plus
3.
2, gonna be 3. 1,
Yep.
1, 0, 0, and 0. And then, you know, I'm gonna take this guy as it is, right? Then I will do what? Shift. So gonna be CAQ. Do you agree?
Yep.
So I'm gonna push with this, right? I have this 0 in my hand. 0 will go here. That 0 will go here. That 0 will go here. That 1 will go here. This 1 will be here. That 0 will be here. This 0 will be here. That 1 is still here, right?
Yep.
Then, oops, I still have 1. What should I do?
Keep adding.
Store,
down.
right? So gonna be A equal A plus M. So in that case, it's gonna be what? 1 and 2, 3, right? 1, 2, 3, right? And then, you know, I have here 1, 0, 0, 1, right? And I have 0 in my hand. Do you agree?
Yep.
Now we're gonna shift.
Again.
So shift it. So gonna be what? 0 here, 0, 0, 0, 1. And then, you know, that 1 will be here, 1 here, 0, 0, right?
Yep.
So now see AQ. Last process. This is what?
0.
0. So then, you know, there is no adding. It's gonna be what? Just shift.
Shifting. Yep.
See AQ. So in that case, it's gonna be what? Somebody tell me.
0, 1, 1,
So gonna be
1,
0, 0,
0, 0, 0,
0,
0.
and then 1, 2, 3, 0. Right?
Yep. Mhm.
What is the output in front of us? This is our output, right?
Yeah.
Let's check this output. What is this output? It's basically those zeros are not affecting me. Do you guys agree?
Yes.
So this one is what? 14.
14.
What was the values? 2 times 7 is what?
14.
Everybody give me $5.
Okay, I think
I
that makes a
understand.
little bit more sense.
Okay.
First time was so confusing.
Yeah, I think I didn't understand because I didn't think about the shifting to the right of all of them. I thought it was just like shifting Q itself.
But anyway, is it a good game?
Yeah, it's easy.
It's a good game, right? So everybody agree with me, it's a good game, right?
Yeah, can we just leave it with division? I think division was pretty much easier.
I can make you division, just give me some time to finish the rest of the syllabus and then, I can give you the rest.
Oh,
This
is division
advanced because I like to give you some advanced stuff, but don't worry.
division the same as this one? I thought division was just
Division is
divided
when
by
we're
2.
shifting left and right.
Okay, never
I
mind.
haven't finished left, right? So
Never
give me
mind.
time.
Yes, never
Anyway,
mind.
we understood there is, first of all, we started with registers, right? We understood registers. Then we started after that building with registers as configuration. Then we took one of the slide of the configuration, we build memory. Then, now we start with shifting. Then we start using one of the shifting in a real application, which is what? Multiplication, right? We haven't built circuit yet, right? You understand what I'm saying?
Yes.
Okay, anyway, so back to the future. So in that case,
Sorry, I was just looking at the previous one, like 13 times 11 one. Where did the carryover come from?
that guy,
Carryover, yeah.
come on, that guy came from 6 plus this value.
Yeah.
6.
So
Got it. Thank you. Got it.
Plus, 0, 1, 1, 0. Add them, gonna be 1. Then 1 plus 1, 0, and there is 1 here, right? 1 plus 0 plus 1 is gonna be 0, and you have here 1, 0. Then that one. Then the carry no more 0, gonna be 1. Then from now on I will push with 1.
So from now on you push with 1. Got it.
But I initially started from 0.
Yeah, you push with 1, but then it becomes 0 again, right?
It will never. You keep push with 1 in that case, because I changed the carry itself. So no more, because it's a fixed thing.
Oh, okay. So we're at the bottom though, like the one that you crossed off, right? Like the 0, 1.
No.
0, 0.
Luckily, that was the last step. So I just shifted and I keep shifting with 1 this time.
Got you. Okay. All right.
But then, you don't read the carry at the end of the day. You just read A and Q as the final output, right? Make sense?
Yep.
A always start at 0 also?
We start with 0.
A does? Okay.
Yeah, it's initial 0. Do you remember the definition I made somewhere here?
Yeah, I was just making sure.
Yeah. Anyway, let's go to the shift logical left. I mean, it's really easy peasy lemon squeezy, honestly, right? Why? Because it's a reversal of the shifting right. So in that case, basically we multiply by 2. So multiply 2. How? Basically, if I have here, for instance, I'm just a 1, 2, 3, right? Then I have here 0, 1, 1, 0. This register is what? Filling with 6, right? So if I push towards the left like this, right? So shifting logically left 1, that means I shifted 1 time sequentially. So then, I will find out that will be what? That 0 will go here. I mean, I have 0 in my hand, right? So then that 0 will be here, that 1 will be here, that 1 will be here. This 0 will be what? Spelled out. You guys agree?
Yes.
In that case, number 6 converted to be a what? 12. So at the end of the day, what we are doing here, multiplying with 2. Then one of you guys, I don't remember, Kushal or whatever, one of you, I don't know, what was the name? The one who said, division. Division is using both of them, shifting left and right.
But then we do like shifting right. 1 was divided by 2, the first one that we did.
No, if you notice, this is not a general rule of division. This is just a corner case of division. Because, you know, if you notice, I divide without caring about any fraction.
That's right. Yeah, without
Yeah,
the
but
decimal fraction.
normal division, you know, you already have the quotient and remainder or whatever, right? So we're gonna
Okay.
have 2 registers and we concatenate them. It's a long story. I'm gonna give it to you, but once I finish the rest of the operation, okay?
Yeah, no worries.
But anyway, now we understand shifting actually, right? Left or right. But we understood what those are, the logical shifting. What about arithmetic shifting? And we understood also, you know, somehow, you know, in direct way that, you know, building this, it needs what? Sequential circuit as a traditional way. Later on, maybe if we have time, or maybe next time, I will show you something that's called barrel shifter, which has been developed by the US Department of Defense and what's called Princeton University. That was made in 1990 something. Okay, anyway, back to the point. So we understood the shifting left, shifting right logically. Let's learn what is this arithmetically. So arithmetically is more used in the sign value. Whatever we have done so far, we don't care that much about the sign. Do you guys agree? Hello.
Yes, sorry.
That means, you know, those registers are unsigned, maybe holding unsigned values, or maybe signed and I don't care that much about the sign anymore, right? But for the shifting arithmetically right, I'm caring about the what's called I'm caring about what the sign. Example, for instance, imagine that, you know, I'm a 4-bit register, and written in this register negative -4. So in that case, I will open my design like this. It is negative, so I have here 1, and it's 4, it's gonna be 0, 0, 1. So this is actually -4 in the sign value. Do you guys agree? Here is the 4, and here is the sign. Make sense?
Yes.
In the arithmetic shifting, we are concerned about the sign, so we have to preserve or the store, or, you know, do our best without losing the sign. So in that case, we're gonna shift with the sign. So we need a process to check what is the sign and start using it. So if I apply shift arithmetic right 1, so that means I will take this one here, then that 1 will be here, this 1 will be here, and this 0 will be here, and that 0 will go out, spilled out. So what I did here, if you notice, I'm not using 0 anymore. I am using whatever written as a most significant, and I push it directly here, and then that will be start shifting like this. Make sense? Hello?
Yep, makes sense.
Yeah, what is the candidates are using this? There is something very famous on the, anyway, there is something famous in the multiplication, but for signing. It's called Booth algorithm. Booth algorithm. I will keep it for now, and if we have time, I can tell you more about it. But it's called Booth algorithm for the multiplication for signing values. Sounds good? This is for signed value multiplication. Anyway, everybody understood what I'm saying so far, right? Is the subject is clear so far, or is there something that's not clear? Oh, he found both algorithms.
Yeah.
I'm gonna give you both algorithms, but not today. But I will give it to you maybe next time. Okay? It's, by the way, it's a piece of cake. Should I give it to you? Or should we start a rotation? Which one you prefer?
Rotation.
Okay, let's go for rotation. So now a rotation. So we have rotation right, a rotation left, rotation right, rotation left. What does it mean, rotation? Basically, you know, that you will never spill out anything. You're gonna be working.
Sorry,
again.
Professor. So what happened with the sign? So that's all it was. So you for the arithmetic method. So for the sign one, you just move it. You use whatever is the most significant bit and shift to the right. That's it. Okay. All right.
But in rotation, this is logically, because I'm not preserving anything, right? So if I go into rotate right, 1, 2, 3, right? 1, 2, 3. So here is, for instance, 1, 1, 0, 0. So what is written in front of us?
6.
Right? So if I go ahead, how many rotation are available here? 4, right?
4,
So
yeah.
rotation right 1, rotation right 2, rotation right 3, rotation right 4, right? You're gonna see something now surprising you. Rotation right 1, right? I'm going towards the right, and whatever I'm spilling out is actually going there. What does it mean? I'm gonna go ahead like this. 1, 2, 3, right? That 0 will be here. Then this 0 will be here. This one will be here. This one will be here. Did you see what I did?
Yep.
So there's no spill out.
There's no spill out. Physically, it's like a ring. Rotation is ring. There is nothing will be spilled out. Anyway, so let's rotate this one more time because we're gonna come now with a very nice conclusion. Then that one will be pushing here. So gonna be 1, gonna be 0, 0, and 1. Right? Then if I take 3, that will be taken like this.
12.
Huh?
Oh, no, sorry.
That one will be here, that one will be here, that will be 0, that will be 0, right? Then I will go here to push one more time. 1, 2, 3, right? That will be here, that will be here, that will be here, that will be there.
Back to 6.
So we need to write some conclusion here, right? Let's see what is the conclusion we have. You will love it, right? A rotation right 4 equal what? The regular register.
Yep.
Right? This is 3, 6, and this is 6, right? Another story. A rotation right 2. No, sorry. Rotation right 1 is equal rotation right 3. No, inverted. I'm sorry. Excuse me, I'm sorry. Leave it as this. That's fine. Just like, you know, rotation 4 is equal the register. Let's do the rotation left. So we're gonna use the same value, and from there we're gonna come into conclusion. Okay. What is the value we use? 6, right? So 0, 1, 1, 0. So I'm gonna apply rotation right, left 1, rotation right, rotation left 2, rotation left 3, rotation left 4. 1, 2, 3, 4, right? And then, you know, I'm gonna do it here. 1, 2, 3, 4. Right? So let's do it left. So that means I'm go like this, right? So that 0 will go back. So here we're gonna be 1, 1, 0, 0, right? Then, you know, that's gonna go there, right? So 0, 1, 1, 0, right? Then one more time. So gonna be 0, 0, 1, 1. Then one more time, right? I think I made a mistake, right?
Yeah, the rotation 2 should be 1, 0, 0, 1.
One second. So, you know, I'm here, right?
That should be 1, 0, 0, 1.
No, but I'm pushing towards like this. It's gonna be 1, 0, 1,
0, 1.
0, 1, right? Then, you know, this one, it has to be cleared also. Then, you know, I go into like this, gonna be
1100.
110, 1100, right? Then if I go like one more time like this, right? So that one will go here, right? So gonna be
And
what?
return to the register.
110. Yes. Make sense to everybody? Hello?
Yes.
So now we can write a very good, nice conclusion, right? Which is that rotation 4 is also equal to the equivalency.
Rotation.
So rotation Ln is equal register, equal rotation right n, right? Look at this. Rotation right n divided by 2 is equal rotation left n divided by 2. 2 is 9. 2 is 9. Right? Look at the fun. Rotation right 1, it was what the value? 3, right? And rotation left 3 is what? 3. Did you see that? So in that case, rotation right n minus 1 is equal to the rotation left 1. And rotation right 1 is equal to the rotation left n minus 1. What do you guys think? Any question? Hello? Hello?
I'm just trying to figure out the last two. N
Okay,
minus
wait,
1.
wait. You know, rotation left 1 is what? 12, right? Rotation right 3 is what?
12.
Make sense? So instead of saying 4 or 6 or 8, you know, I just make it n. So what does it mean? Imagine the phone, you know, let's say that my register 128-bit, right? So, you know, if you know rotations left 128 divided by 2, it's going to be rotation right 128 divided by 2, right?
I got an email.
If somebody telling you that, you know, rotation right, if you have in your hand rotation right 126 in 128-bit, so a rotation left 2 is equal what?
Uh, 120. No, wait, 126, right?
Yeah, it's gonna be n minus 2.
126.
Make sense? How can we build a circuit from whatever we learn from the configuration doing this? That's not really hard, right here. Right? You can make it P, pull, and you push sequential, and you loop back, and you can just make rotation towards the right, and still you can get the rotation left. Make sense?
What's your enable or select over there?
It's my select. I'm the one who will decide, right? I can, you know, let's say that I would like to load data here sequentially, right? So I can put 0 here. Then I can make it shift. So this circuit can do a what? Shift towards the right, and it can rotate left and right. Somebody will tell me where is actually left? You know, you have just rotating right. But you know, I know from the trick here, I can also from the right, I can rotate left. Make sense?
Yeah.
Okay, so end of the day, humans really like everything to be done really fast. So we don't care that much about, it's cool that, we build in our brain something that's called sequential circuit, and, we make the in out sequentially, and then, we have the parallelism from the people, or, CPO piece or whatever, but, also there is another way for you to build shifter using combinational circuit, not even sequential circuit. And that will be our next topic on the coming Monday, which is barrel shifter. Then we finish barrel shifter. We will see what else we have for register and configuration design. We can go through process design, and I think I already give you like a set of handwriting notes under the week 13. The file is called registers. Have you seen it?
No, but I'll go look at it.
Go in a Blackboard, week 13, supporting materials, you will find it there. Okay, so I'm gonna put the notes, of course, of this today, and then, after that we can go back to the sequence detector, so we can make a finite state machine for sequence detector. And if we have enough times, if you want, I can go through some of the building processors, or even, look into Verilog if you want. Sounds good?
Thank you, sir.
Okay, so it was my pleasure to talk to you today, and I wish you guys the best of the
Wait, quick question.
2 questions.
Sorry, you can dismiss the class. I just had a question for you.
Who would like that?
So for let's say a finite state machine, right? That has like 4 is it 4? 5 bits?
Yeah,
So for a 5-bit, right?
it means 32 states.
Yes, 32 states, right? But the four of them are actually it's a 4-bit with an enable, right?
Yeah,
How would I do that without having a 5R K-map? Can I do that without a 5R K-map?
yeah.
What would be the right stepping stones?
Do you remember when I made the counters in front of you? And I was using enable, and I didn't count the enable in the states. Do you remember that?
You did that?
Yes.
I knew it happened somewhere. Do you remember what?
It's one
When
of the
did we do that?
because of the counters. Just look at it, okay?
Okay, I'll
Okay.
go look at it.
Okay, anyway, so it was my pleasure to talk to all of you, and I wish you guys the best of luck. And somebody, Professor, are you posting grades after class, after all? I will be posting, don't worry. I'm gonna post everything. Okay, so no worries. Anyway, so I wish you the best of the rest of the day, and I wish you a wonderful weekend as well. And I will see you guys on Monday. God bless all of you.
Have a good one, Professor.
Thank you. Bye-bye.
Patsy.
All right, thank you, Professor.